Yes. Welcome back. So today let's start with clamper circuits. All right. Okay. Is it visible? The screen? Can anyone confirm? All right. Fine. So far we studied clipper circuits, right? Clipper circuits are used uh, to shape either the positive half of the input or the negative half of the input, or you could shape both the halves of the input. So clipping circuit is basically wave shaping circuit. Okay. On the other hand, clamper circuit, okay, is also wave shaping circuit in the sense that it will not chop or it will not clip the waveform. Okay. Instead, it simply shifts the input waveform. Okay. So clamper circuit shifts the input waveform. Input waveform. Okay. So normally, the input waveform we represent in such a way that the input waveform, starts from 0 volt level. Okay. Or you could say the input waveform is having 0 volt DC offset value. So this is 0 volt. Okay. Or you can also say that the waveform is starting from origin. Okay. So whenever the waveform starts from origin, we would say 0 volt DC value. Okay. 0 volt DC value. But sometimes in analog electronic circuits, or rather in practical applications, it's desirable to shift the waveform. Okay. So when I say shift the waveform, one can shift the waveform either in the positive direction or above the reference axis, or one can even shift the waveform in the negative direction or below the reference. Okay. So whenever you shift the waveform above the reference axis, it is considered as positive shift. All right. It is considered as positive shift. On the other hand, if you push the waveform below the reference axis, it is considered as negative shift. Negative shift. So accordingly, the clampers, see, in the beginning I said clampers are meant for shifting the waveform. Okay. When you say shifting the waveform, one can shift the waveform in the positive direction or one can shift the waveform in the negative direction. So in clampers, there are two types. Okay, can you guess? A positive clamper, okay, and a negative clamper. A negative clamper. Okay. Now, why do we need to shift the waveform? Why to shift? Okay, by doing so, do we get any advantages? Okay. Now, in our electrical circuits, let's say, for example, transformer. So for a transformer, we would expect our waveform, the input waveform, starts from 0 volt level. That's because if your input waveform is having any offset value, let's say plus VDC or minus VDC, the transformer core gets saturated. Okay, so that is very objectionable. So in electric circuit, very widely used waveforms will not have any DC offset value. But on the other hand, in some electronic applications, we go for this shifting of waveform. Such application, one of the application would be something like your composite signal, basically. Okay, your composite video signal. Okay, so what we do, this video signal, okay, is sent from the transmitting station. Okay, and that video signal is then received by our setup box, right? It's your setup box, and the setup box will transmit the same signal to the television. Okay, to the television. So this is what your what you say video broadcasting, I would say schematic. All right, this is now when you say video signal, what are the subcomponents of video signal? The video signal will have, you know, three signals. Okay, this video signal is superimposed with audio signal. Okay, and then sync signal. I'll come to it. What do you mean by sync signal? Okay, which is also called as synchronous signal. And you will also have luminance signal. Okay, so this luminance signal basically consisting of the color information. Okay, later on that color information gets the shape of a picture. So you can see that your video signal is consisting of three signals. Okay, now remember one thing, all these three signals are alternating in nature. Now imagine the condition that if you pass all these three alternating signals with, you know, zero reference. Let's say this is your second signal, and let's say this is your third signal. So if you were to pass, so this is signal 1, 2, 3, and this is your time axis. Okay. If you were to pass all these three signals with, let's say, zero offset value, then what will happen is the person or the operator who is sitting in the, say, TV station will have, you know, a lot of trouble in identifying the signals. That's because the operator need not be an electronics engineer. The operator could be a layman. Okay, normally the operators are laymen. So they will not understand what should be the amplitude of audio signal, sync signal, luminance signal, etc., etc. So in order to provide a kind of foolproofing, okay, foolproofing means the crude understanding is any fool can follow. Okay, the foolproof terminology which is used in engineering meant for, you know, something like any fool can understand. That means to say the operator need not have the technical understanding of the communication signals. So in order to achieve foolproofing, what they will do is, okay, let's say the audio signal, okay, let's say the audio signal is broadcasted at 0 volt level, and let's say your say luminance is broadcasted, let's say plus volt VDC level. Okay, this is your luminance. Okay, and say suppose your let's say your synchronous signal, if let's say it is being broadcasted at minus VDC level, you know, the operator, this is sync, right? This is sync signal. This is sync signal. Okay, the operator can easily distinguish, you know, the three signals. So if any, sometimes you must have seen in your television, right? You know, there will not be any proper sync between video and the audio. Okay, so whenever this sync problem comes into picture, the operator can communicate to the station master about the problem. Okay, so what will happen is for proper sync, you know, there will be a fixed plus VDC level and minus VDC level. If at all the signal gets drifted from, you know, this plus VDC level and minus VDC level, then there will be some kind of syncing issues. All right, so whenever there is syncing issue, what the layman has to do is he has to just track this plus VDC and minus VDC level, and he can just communicate this level with the station master, and station master accordingly will correct the signals. Okay. Now, what you have understood from this practical explanation is that by shifting the waveform, you can achieve something known as foolproofing in case of the broadcasting scenario. All right. So clampers are widely used to shift the waveform. Okay. So clamper, as of now, you can assume it as a black box. Okay, this is your clamper. So to the input, across the input terminals of the clamper, you will give a 0 volt level signal. Okay, whereas across the output terminals of the clamper, you can get either positive DC, positive clamp, or you can also get a negative clamp. All right, so that's the brief introduction of the clamper circuit. Okay, I'll just take a pause now. Now, do you have any doubts in clamper operation? Okay, don't worry about the technical explanation. The practical usage of clamper, did you understand? Okay.
Yes, sir.
Okay, all right. So fine. So that's about the brief introduction of the clamper. Okay. Now let us look at the engineering aspects of clamper. That means to say the designing and the analysis part. All right. So clamper circuits. Okay, I'll just write classification. Just like clippers, even clampers are classified broadly into two types. Okay, biased clampers and unbiased clampers. Okay, in case of biased clampers, VDC exists. In case of unbiased clampers, VDC doesn't exist. All right. Now, in both biased and unbiased clampers, you can have, as I said previously, you can have positive clamper, or you can also have a negative clamper. All right. Now, when you take out the analysis, okay, when you do the analysis of a clamper circuit can be made on the basis of ideal diode, or it can be made on the basis of practical diode. All right, fine. So fine, let's jump into the analysis part. All right. So first, let me consider, let's say, okay, before jumping into the circuit, let me talk about design constraint. This is very important, okay, because if you obey the design constraints, then only you can achieve a successful clamper operation. Okay. So this design constraints are on the basis of rule of thumb. Yeah. Have you heard of this rule of thumb in the previous semesters or something? You can just write yes or no. Rule of thumb. Have you heard of rule of thumb? Yes or no, you can type. Okay, so this rule of thumb is nothing but this rule is not being proposed by any mathematician or statistician or a scientist. Okay, so rule of thumb is basically nothing but the experimental results are converted into kind of the rules. There is no proper origin for these rules. Okay, so you observe the physical phenomenon. Okay, and from the physical phenomenon, you propose that, okay, if this is the case, this is what is going to happen, something of that kind. Okay, so rule of thumb is nothing but the rules based or rules derived by observing the physical phenomenon. Okay, so there is no mathematical proof to support rule of thumb. Okay, so it is from the observation. So I would write from the observation. From the observation. Okay, so the same observation may lead to kind of empirical relations. Okay, you must have heard about empirical formula, right? So this empirical formula are derived from the observations itself. Okay, so empirical relations or rule of thumb, it conveys the same meaning, that is, from the experiments you are generating the theory. Okay, vice versa is not possible. Okay, fine. So in case of clamper, okay, clamper. So clamper circuit consists of diode, capacitor, and load. Okay, diode, capacitor, and load. Okay, let's say R. So it is consisting of only three elements: diode, capacitor, and load. Okay, now when you have to design a particular clamper circuit, okay, you cannot simply choose okay, diode doesn't matter. Okay, diode can be any diode. Okay, can be any diode. Okay, in the sense it can be say, let's say BY127 series. Okay, or it can be let's say 1N4007 series. You have different types of PN junction diodes. Any diode you can choose for your clamper operation. So there is no restriction on the selection of diode. Okay, but when it comes to capacitor and load resistor selection, okay, you have restrictions in the sense you cannot simply take some 1 microfarad capacitor and let's say some 100 ohm resistor. No, you cannot choose just like that the capacitor and resistors values. The capacitor and resistor values, okay, I'll just write C and R values are chosen on the basis of time constant. Okay, yeah, I just wanted to know, have you come across a word called time constant in basic electronics? Yes or no, you can type. Have you come across a word called time constant in basic electronics or in your 11th or 12th? You can just type yes or no in the chat box. Okay, you are saying yes. Okay. Please be attentive, right? Please be attentive. It is not like you just log in and you just do your stuff. Okay. All right. Now this time constant refers to the product of resistance and capacitance. Time constant is popularly denoted by a symbol called tau R into C. Okay, so the product of resistance and capacitance is nothing but the time constant. Okay, this is in case of capacitive circuit. In case of inductive circuit, this is for capacitive circuit. This is for capacitive circuit. All right. In case of inductive circuit, the same time constant tau is R into L. This is for inductive circuit. Inductive circuit. Okay. Now, as of now, I'll pay attention to only capacitive circuit because your clamper is consisting of a capacitor, not an inductor. Okay. And you see this time constant, what you say, the term, this is not for the first time you are listening. All right. In the basic electronics, okay, you have studied about the capacitor filter. Okay, capacitor filter. Okay. Let's say this is your rectifier. Okay, this is, let's say, your rectifier. This is your rectifier. All right. This is the input to the rectifier. Okay. And output of the rectifier will be kind of rippled output, right? This is your output. So what you do in case of rectifier is that you connect this rectifier, what do you call the rippled output to a circuit called filter. Okay, so this filter circuit is consisting of two major elements, a capacitor and a load resistor. And across the load, whatever output you are going to measure will have kind of smooth DC shape. So this is your V0. Okay. Now the filter circuit. This is your filter. This is your filter. So this filter circuit is basically gives the time constant of the circuit. Okay. So the product R into L, okay, RC I will write, gives the time constant of the circuit. Okay. Now, what is this time constant? Why this is called as time constant, the product R and C? This is called as time constant. That's because the values of R and C determines how quickly the capacitor is going to lose its charge or how slowly it is going to lose its charge. So there is something like, time behavior, right? So the losing of charge is related to time. The capacitor can quickly lose its charge or the capacitor can, retain its charge for a longer periods of time. So since the time is coming into picture, that's the reason, this performance parameter is called as time constant of the circuit. Okay. Now, what implication it has on the wave shape V0? Okay. Let's say you choose low time constant. Low time constant. Okay. Example. Let us say R is 1 kilo. Let us fix the value of R. And let us say capacitor is 0.1 microfarad. So when you multiply R and C, you will get some time constant tau 1. Okay. Now, if at all you were to choose very low capacitor value, which is going to give you very low time constant tau 1. So if your time constant is very small, then your rectifier output could be something like this. Okay, this I will write V0, and for your understanding, I'll write filtered output. Filtered output. So if your time constant is very small, then your waveform could be something like this. So on, so forth. Okay. So what is happening over here is that somewhere the capacitor gets charged. Okay. And the moment the input waveform starts to reduce from its maximum value, the capacitor starts to discharge. Okay, and this continues once it is going to continue one cycle after the other. So basically what is happening, you by choosing a lower time constant, you are allowing the capacitor to discharge. Okay, so your output waveform basically toggles between, okay, Vmax level and Vminimum level. Vminimum level. So this change in voltage, that is Vmax minus Vmin, okay, we call it as ripple voltage delta V. So this is your ripple voltage. Ripple voltage. Okay. For a good DC, for a good DC waveform, this ripple voltage delta V should be very small, very small. Okay. So that's how we talk about the goodness of DC. If delta V is very small, we call it as a very good filtered DC. If delta V is very large, then we would say the rectification is not good and there's too much of ripple in the output. Okay, so you have understood now that a lower time constant can give you unwanted fluctuations in the DC waveform. Okay, that is called as the ripple voltage. Okay. Now let us see what will happen if you were to select a high time constant. High time constant. Okay, let's say tau 2. Okay, in the previous case, let us take it as tau 1. Okay, example. Let's fix R value at 1 kilo ohm only. However, let us take C value with a very high capacitance value. Let's say 10 microfarad. Okay. So product R and C will give you the time constant, right? So we get T2 as R into C, which is high compared to the first case. So by choosing a very high time constant, okay, you can control the discharge interval of the capacitor. What you can control? You can control the discharge interval of the capacitor. Okay, so the capacitor or the entire circuit will have now more capacity to retain the charge. So by retaining the charge, you can limit the discharge period of the capacitor. All right. So this is your output. Again, let me write. This is your filtered output. All right. So in this case, what happens is that, let's say the capacitor charges, okay, to this extent, and then it discharges. Okay. Then it charges, then discharges, charges, discharges, so on, so forth. Okay. So this is your Vmax, okay, and this is your Vmin, Vminimum. And if you were to take out the difference between Vmax and Vmin, you would see that the change in voltage, delta V, is very small, very small. Okay, so earlier it was very bad. Okay, so this was your delta V. Now, you have reduced to a smaller value. That's because the discharge period, if you see, the capacitor, is getting discharged only for some extent. Okay, in the previous case, the capacitor was getting discharged for a larger extent. Now it is getting discharged to a smaller extent. Okay, likewise, if you were to do something known as parametric variation. So parametric variation, as in you are fixing one parameter constant and the other parameter you are varying. Say for example, if you were to select a very high time constant, very high time constant, let's say tau 3. Okay, so say R is equal to 1 kilo ohm and C is equal to, let's say, 100 microfarad. So whatever time constant tau 3 you will get, that is R into C, will be extremely high, extremely high. So by fixing a very high time constant, you can expect a waveform of this kind. Okay. So this is your delta V naught. Okay, this is your V naught. okay, where delta V is equal to 0. That's because there's nothing like minimum and maximum. The waveform is almost, staying constant. So when the waveform is perfectly a straight line such that it is parallel to the x-axis, what happens? Delta V becomes 0. That's because V maximum exists. Okay, but V minimum in this case is 0. Okay, so what have you achieved basically? By increasing the time constant, you have achieved a pure DC. Okay, now why I had to explain all this? I had to explain all this because your clamper circuit works on this condition. So for a successful clamper operation, a designer must choose extremely high time constant. Okay, so in the given example, I had chosen three time constants: T1, tau2, and tau3. So out of these three taus, for a clamper operation, you are supposed to use tau3. So tau3 is chosen for clamper operation. Okay. Now, if you look at the waveform of time constant tau3, the waveform resembles battery voltage. The waveform, it resembles battery voltage in the sense, if you were to take out the waveform of a DC cell, okay, let's say this is your DC cell, positive and negative. Okay, if you connect a DC cell to a CRO, okay, graphical device, you would see that the output of DC cell is constant, okay, constant. There will not be any variations in the cell potential, in the sense it is remaining constant. Okay, so if you compare, the first waveform with the second waveform, you would see that they are more alike waveforms, right? So in our explanation, what we do is, by choosing a high time constant, the capacitor is treated as dash. Can anyone type the answers? By choosing a very high time constant, the capacitor can be treated as dash. The capacitor can be treated as a battery. Absolutely. Okay, so the capacitor can be treated as a battery. Okay, so you have to convert that particular capacitor into an equivalent device called battery, because if you can convert that capacitor into a battery, then only you will be able to add either dash DC and dash DC. Can anyone type? If you convert that capacitor into a battery, then only one can shift the waveform in the positive direction or in the negative direction. Positive direction is possible if you achieve positive DC, and you will be able to shift the waveform in the negative direction, provided your capacitor is providing you a negative DC voltage. So this is the basis of, or the base for, your clamper circuit. Okay, so whatever capacitor you are going to use in your clamper circuit is regarded as a battery in our analysis part. Okay, so that is possible by choosing high time constant. By choosing high time constant. Okay. Now let me come to the statement of rule of thumb. So the rule of thumb says, your time constant. Okay, time constant T. Okay, so this is tau. Tau is equal to RC. Your RC, okay, or rather I put it in this way. Hold on. Okay, so product 10 times RC, okay, should be very much greater compared to capital T. Okay, so this 10 time RC refers to tau. Okay, what is tau? Tau is the time constant. Okay, so this tau should be very much greater compared to capital T. So this capital T is nothing but time period of input Vi. Okay, so what is the meaning of this? Let's say you have frequency. Let's say frequency of AC input is equal to 1 kilohertz. Okay, so the time period is T is equal to 1 by F, or it is 1 by 1 kilohertz, which is equal to 1 millisecond. So time period of the given AC input is 1 millisecond. Okay, so that means to say, when you have to choose the time constant for this circuit, you should make sure that that time constant of the circuit is extremely high in compared to the time period of the waveform. Say for example, let's say I choose R is equal to 1 kilo ohm and C is equal to, let's say, 100 microfarad. Okay, so what do I get? I get RC as 1 kilo into 100 micro. All right. So that's about 0.1. So it is 0.1 second. All right. And as per rule of thumb, you need to multiply with 10. So 10 times RC is actually 1 second. 1 second. Okay, now you do the comparison. So tau, you compare with capital T. How much did you get tau as? You got tau as 1 second, and this tau you need to compare with time period. Okay, and time period is just 1 millisecond. 1 millisecond is basically 1,000th of a second. Okay, so you can say that the condition is satisfied. Because this tau is way higher than the time period of the input waveform. Okay, this is what is required for your clamper operation. All right, so this being the introduction, probably tomorrow I can take up the practical clamper operation. Okay. Any doubts, you tell me in this. Did you understand? Do you want me to repeat anything? You just let me know. Okay. All right. So the summary of today's class is that once the capacitor is charged, it can be treated as a battery, and the capacitor will not discharge, capacitor will not discharge in the future, okay, or in the upcoming input cycles. Okay, so this is very, very important. So in the next class, I'm going to teach you the operation of clamper on this basis. Okay, once the capacitor is charged, okay, by satisfying this condition, that is by choosing a very high time constant, it cannot discharge, for any of the upcoming input cycles. Once charge means it is battery. Okay, throughout the clamper operation, the capacitor is treated as a battery. Okay, so that is what you need to fix it in your mind. Okay, no way that the capacitor is going to discharge. Okay, this I can demonstrate in laboratory also. Okay, maybe not the next lab, probably the week after that, I will demonstrate this in the lab also. Okay, but as of now, please consider it as a battery. All right. That's all for the day. Tomorrow, let's meet. Okay. So today I will circulate a quiz. Okay. Thank you.
Thank you, sir.